Ever wondered how to find the pH at the equivalence point of a titration? Well, stay tuned. You're in luck. That's what this video is about. When you need to find the pH at the equivalence point of a titration, one of the most important things is to realize that whether you're starting with a weak acid or starting with a weak base, when you titrate it, you convert all of your weak acid into the conjugate weak base, or you convert all of your weak base into the conjugate weak acid. So all of your starting material, whether it be an acid or a base, at the equivalence point is converted into its conjugate. So our process for finding the pH at the equivalence point is going to be to first figure out what the concentrations are for either our weak base or our weak acid, whichever the conjugate is. To do that, we're going to use the fact that this is a mole-to-mole transition. So however many moles of acid we start with, that's the number of moles of base we end up with, or vice versa. However many moles of base we start with, that's the moles of acid we end up with. We also have to account for the volume increase, since doing a titration we'll be adding an additional acid or a base to make the reaction go. Once we've got that concentration, then we need to solve the equilibrium that occurs at the equivalence point. So we're going to be either solving a weak base equilibrium or we're going to be solving a weak acid equilibrium, depending on the type of problems that we have. In either case, we're almost certainly going to be using an ice chart to figure out this problem. Okay, so here is an example from Aleks. And in this example, we are given 190 milliliters of 0.224 aniline, and we are titrating that with 0.7965 molar HBr, which is a strong acid. Okay, so let's go ahead and calculate. We'll work toward calculating the concentration of anilinium that we end up with. Okay, that's the conjugate acid of the weak base aniline. So aniline is a weak base. Okay. So if we use the information that we're given, the volume and the molarity, and we calculate that out, we know that we have 0.224 moles. I'm sorry, that's the molarity. When we calculate out the number of moles, we have 0.04256 moles of aniline. And of course, then that same number of moles is going to be converted into anilinium. Okay. We could also go ahead and calculate the equivalence volume, so we know how much the volume is changing. And so to calculate the equivalence volume, we're going to start with molarity of acid, volume of acid equals molarity of base times the volume at the equivalence point. And if we do that, we calculate the volume at the equivalence point to be 53.43 milliliters. That's the amount of base that we're going to add. Okay, so we can combine these two things to determine our concentration of the anilinium ion, which I'm just going to list as An+. So anilinium ion concentration is going to be the number of moles, 0.04256 moles, and we have to divide by the total volume at the equivalence point, which is going to be 0.190 plus 0.05343. And that gives us a concentration of 0.175 molar. Okay, so that's our first part where we've calculated the concentration of the aniline. So the second part of this considers the equilibrium that the aniline will establish. So the aniline will react with water. The aniline itself will be a weak acid. So it's going to give H3O plus and AN. Just to be righteous about everything, I'm going to go back and include my H in the notation for the aniline ion. Okay. So now we'll do our ice chart, and we'll start with an initial concentration of 0.175. We don't care about water. We don't have any of the other stuff. And we'll do minus X plus X plus X, 0.175 minus X, X, and X. And at this point then we're ready to solve the equilibrium. So we could write Ka then is equal to X squared over 0.175 minus X. And Ka for the aniline ion is equal to 7.41 times 10 to the minus 10. Now Aleks did not give us that. It gave us the pKb for aniline. So we had to do a little bit of work to get to the Ka for the aniline ion. In either case, we've got this equilibrium that we need to solve. I would suggest trying to ignore X in the denominator. And when we do that, that leads to an easy solution of X being equal to the H3O plus concentration equal to 1.14 times 10 to the minus 5. And that gives us a pH equal to 4.94. Okay, so the general steps, we need to make sure that with every problem we are converting our weak acid or weak base into its conjugate, that we're finding the concentrations, and that we're solving the relevant equilibria. If you found this video helpful, go ahead and smash that like button on YouTube and then follow the channel Darn It Dave. Sure would appreciate it.